4.10 Antiderivatives. This whole chapter we've worked on calculating derivatives and using them for various applications. Now we ask, how do we undo that? So if we're looking at a function f, can we find the function whose derivative gave us the function f? For example, f of x equals 2x. I'm looking for a function capital F so that when I take the derivative of it, the result is the function lowercase f. So in this problem, where we're looking at f of x equals 2x, I'm looking for a function that will fit inside of these square brackets so that when I take the derivative of it, I get 2x. Well, this 2 in front of the x probably used to be the exponent before the derivative was calculated, so maybe it was x squared. And then we confirm, yeah, x squared, the derivative of that is 2x. Perfect. And what about any other functions? Is there anything else I could plug into these brackets so that I would still get out 2x? Well, I can't use x cubed. I can't use the square root of x. I can't use sine of x. So you might think, nope, x squared is the only one. But what about x squared plus 3? X squared plus 3 still has the same derivative, and that's because 3 is a constant. And we know the derivative of a constant is equal to 0. So the capital F function that we were looking for, that has to be x squared plus any constant you can imagine. All of these functions, x squared plus c, those are called the antiderivative for the function f of x equals 2x. Theorem 4.14 says that in more rigorous terms, but it basically says the general form of an antiderivative includes this unknown constant c because we know that derivatives will make constants disappear, so if we're working backwards, we need to consider that. Let's practice on a couple of functions. I'm looking for a function that fits in these brackets so that the derivative comes out to be 3x squared. Well, the 3 in front of this x probably used to be the exponent, so we'll try x cubed. And in fact, that works perfectly. X cubed, take the derivative, you get 3x squared. But remember, there's a constant that's kind of hiding in there that we would have never known existed unless we knew more about derivatives. So the antiderivative function we're looking for is x cubed plus that constant c. This next function is actually one we're going to skip because it requires you to understand the natural log function, or ln of x, and we actually don't cover those in Calc 1, we cover them in Calc 2 at Merced College, so we're going to skip that one and move on to problem C. This is asking us to find the function whose derivative is cosine x. Well, we know that sine x has a derivative equal to cosine x, but we also know sine x plus a constant has that same derivative. So our antiderivative in general form will be sine x plus c. Our indefinite integral definition says that you can integrate the little function f and it will find you the capital F function, the antiderivative function, with that constant that could have been there. And maybe that constant was equal to 0, but we don't know that, so we have to put plus c just in case. Terminology, let's make sure we understand what we're writing here. The f of x function, the thing we're integrating, we call that the integrand. X is the variable inside of that function. We call that the variable of integration. And then, of course, capital F is the antiderivative. When we first learned about taking derivatives, we learned a shortcut for power functions. So let's recall that when we learned how to take the derivative of x to the nth power, we said that you would take in the exponent, multiply it in front, and then subtract 1 from that exponent. So we're multiplying and then reducing the exponent. We're going to do the exact opposite for integration. Instead of n minus 1, we'll do n plus 1. Instead of multiplying, we will be dividing. And instead of multiplying by n, we're actually dividing by n plus 1 so that we can undo the operation of differentiation. There are other rules that we can use, shortcuts. We know that the derivative of a constant is 0. So if we were to try and integrate 0, we would get a constant back. If we wanted to integrate a constant, then we know that we're going to get a variable times a constant back, and that's because the integral of a constant could be looked at as the integral of a constant times x to the 0 power. And so when you add 1 to that 0 power, the x has now an exponent of 1. We also know our power rule, so we have the derivative power rule, which gives us the power rule for integration, adding 1 and then dividing by that new exponent. We know that the derivative of sine is cosine, which means if we wanted to reverse that, we could take the integral of cosine and we need to get sine back, and we do. So everything in the left column is the derivative rules that we've learned before. Everything in the right column is a new integration rule that's helping us get back to the original function. One of the types of problems that we'll do in this section is where we verify the statement that's given to us. So if we're given a statement like the integral of f of x is equal to capital F of x plus c, we might need to test that that's true, and the way that we're going to do that is by showing that the derivative of what's presented as capital F, it matches the thing that's inside of the integral. So in this problem, capital F is the x sine x plus cosine x. We can see that because it matches up with the form that the problem says it's written in. Little f, that's the integrand, that's the thing inside of the integral. I see that as x cosine x. So all we need to do is take the derivative of capital F and then show that it equals little f. So let's try it. We'll take the derivative of x times sine x plus cosine x. That first term, to take the derivative, we need the power rule. So that would be 1 times sine x plus x times cosine x. Then we need to take the derivative of that second term. Derivative of cosine x is negative sine x. See if we can clean this up a little bit. Positive sine x minus sine x, those cancel each other out. We're left with x times cosine x, and that's exactly equal to what we have in our integral. So we identified the antiderivative based on how the statement was written, took the derivative of it, and then we showed that it's equal to what was inside of the integral. So we appropriately found the correct antiderivative. We know that with derivatives, the sum or difference of two functions, we could add them together, then differentiate, or we can differentiate and then add the derivatives together. So it only makes sense that antiderivatives work the same way. If capital F is the antiderivative for little f, and capital G is the antiderivative for little g, then the sum of f and g should also be the sum of the antiderivatives of f and g. And then also we have a statement down here that says constant multiples are able to be factored out. So if k is being multiplied to f, then the antiderivative should also have that multiple of k outside of it as well. All right, we're going to try a couple of these integrals just by using the integration rules from the table that was on the previous slide. So we're not playing this guessing game anymore. We're going to reverse these power rules. So integrating this first polynomial function, we're going to do it term by term. 5x cubed. So I'm going to take my 5, multiply it out front. My x cubed, I'm going to add 1 to the exponent and then divide by the new exponent. Then we're going to move on to the next term. This has a -7 out front, so I'm going to pull that off and then look at the x squared, add 1 to the exponent, divide by the new exponent. Next term is 3x, so I'm going to write the 3 as a multiplier outside. X has a power of 1 already, but we're going to add 1 to that and then divide by that new exponent. And then we have one term left, and that's the 4, so I'm going to do plus 4. Now technically, we could look at this as x to the 0 for the original exponent, because x to the 0 is 1, but then we're adding 1 to that from the process of integration, and then dividing by our new exponent. And then we can clean this up. So instead of x to the 3 plus 1, we can write that as 5x to the 4th, and the denominator could be simplified to be a 4 as well. And then we have minus 7x cubed over 3 plus 3x squared over 2 plus 4x. Ooh, and I did a big no-no here. I forgot the most important part. I wouldn't say most important, but a very important part. Every time you integrate, the final thing you should write down is plus c for our final integral value. So our antiderivative, the f of x, is equal to 5x to the 4th divided by 4 minus 7x cubed divided by 3 plus 3x squared divided by 2 plus 4x plus that constant c. Moving on to our next problem here. In order for us to apply any of the integration rules that we have, we first need to clean up the integrand with some algebra. So I'm going to separate the numerator. Instead of x squared plus 4 cube root of x being in one fraction, I'm going to write these as their own fraction, same denominator, x, because that will allow me to simplify. X squared over x, that's the same thing as just writing x. 4 to the cube root of x, well, let's rewrite cube root of x as x to the 1/3 so that we can simplify the exponents. X to the 1/3 divided by x is actually going to look like x to the -2/3. Now we can do our reverse power rule for each of these terms, starting off with x. It has an exponent of 1 to begin with, but we add 1 to that, then divide by the new exponent. Moving on to the next term, we have 4x to the -2/3. That will become 4x to the -2/3 plus 1 divided by -2/3 plus 1, and then of course our plus c. And we'll clean this up the best we can. X squared over 2 plus, well, let's add our exponents. -2/3 plus 1, that's going to look like a positive, positive 1/3. Sorry, I forgot my 4. Whoopsies, dropped my pen. 4x to the positive 1/3 divided by 1/3. We don't like fractions inside of fractions, so instead of dividing by 1/3, I'm going to flip that and multiply so that my final answer is going to look like x squared over 2 plus 3 times 4, or 12, x to the 1/3 plus c. Now each one of these polynomial terms is just going to be using the power rule in reverse, so I'll let you try C on your own. Part D, in order for us to integrate this one, we need to go back to that table that we had. Let's go back. Where did it go? My slides aren't letting me go back, so we won't. But we need to look on that table and find the antiderivative for tangent x times cosine x. And looking, I don't see one. So we can't use the table here. Sometimes you can. Instead, what we'll do is try to simplify again what's inside of the integral. Tangent is the same thing as sine x over cosine x times cosine x, because there was a second factor there. Oh, there we go. Our cosine x divide off, so we're really looking at the integral for sine x dx. We go back to our table. This time we can find a shortcut indefinite integral for sine x. It comes out to be negative cosine x plus c. The last idea in this section is the initial value problems. So initial value problems they involve a differential equation. In this case, the differential equation we're looking at is dy dx equals sine x. A differential equation is just an equation that involves a function and that function's derivative. So dy dx is the part of this that makes this a differential equation. These problems are very interesting because sometimes all we know is that the derivative is given to us and we need to reverse backwards. So here we're asking what function y makes this true. So if we start off with dy dx is equal to sine x, we are essentially going to integrate to undo the derivative that was already done. And we're integrating with respect to the independent variable x. If we had d dx and then we undo that, then we're really left with y. So on the left-hand side, we're left with y. On the right-hand side, we're integrating sine x, which we just said was negative cosine x plus c. Now, technically, there are two integration symbols. And when I first learned about this, I thought if there's two integration symbols, then we are integrating two separate times. Therefore, we should have two separate constants. Meaning I should have y plus c on the left and negative cosine x plus a different constant on the right. So maybe we would even give these two c's a subscript to say these are different numbers. They don't have to be equal. But the reason why that's not necessary is because I could simplify this by combining my constants. And then I could say something like the sum of those two constants is the constant c with no subscript. So don't get hung up on the constants. We can always group them together and rewrite them as one number. In the end, we don't need to have them sprinkled throughout our equation. All right, back to solving our initial value problem. We started off with a differential equation. We integrated it to find the function y, the antiderivative function y, and now we're going to plug in this known value. We call it an initial value problem because it tells us what the function looks like when you plug in 0, or the initial starting point. So we know that y with 0 plugged into it is equal to 5. So if I did y of 0, that would look like negative cosine at 0 plus c. And we know that y at 0 is equal to 5. So we can solve this equation, so you can ignore the y of 0 notation on the left. We can solve this for c. So negative cosine at 0, that's going to look like negative 1 plus c, that's the left side of our equation, and we said that's equal to 5. Add 1 to both sides. We find that c is equal to 6. The final answer to an initial value problem is the exact function that solves this situation, and that's the function y, a function of x, that looks like negative cosine x plus the constant 6. We found exactly which constant made this true. If we picked any other constant, the the initial value wouldn't work. So the C that we picked is the only one that makes this true. Here's another type of problem that's kind of an initial value, but some people would argue it's not, because initial value means you're plugging in 0 for like the first moment or the initial value. But otherwise the process is the same. We start off with some differential equation, and then we integrate both sides of it with respect to the independent variable. The integral of dy dx, well, that gives us the function y back. The integral of 3 over x squared, maybe we need to rewrite that as 3 times x to the negative 2. That way we can see that we are taking that x to the negative 2 power and adding 1 to it, and then dividing by that new exponent. And then don't forget the plus c. So the general solution is going to look like 3 times x to the negative 1 divided by negative 1 plus c, which we can clean up even more, write it as negative 3 over x plus c. But we're not done yet, because c is unknown. We need to solve for c. To do that, we'll use the given information. We know that if we plug 1 into this function, that's going to look like negative 3 over 1 plus c, and then that should produce the output of 2. This time, everything in the equation has been substituted. We only need to solve for c. So we have negative 3 plus c equals 2. Add 3 to both sides. We get c equals 5. So our final answer is y equals negative 3 over x plus 5. That is the function that solves this initial value problem.